In this video, I'll cover some issues on electrical safety when working with old electronics like tube radios. I'll say something about the dangers of electricity as well as some non-electrical dangers when working with old electronics. We'll talk about how to work safely on vintage electronics and some component and circuit modifications you can make to make them safer and less prone to failure. This information will be applicable to electronics like vacuum tube-based radios from the 1920s through 1960s, as well as some amateur radio and test equipment. While I'll make mention of some other equipment like televisions and radio transmitters, this equipment has risks and dangers unique to them that are outside the scope of what I can cover here. I do have to preface all of this with a big disclaimer. Working with AC line-operated electronic equipment is dangerous and can lead to injury or death. I can't be held responsible for any advice given here. Do your own education and research and only work within your comfort zone and level of knowledge. First, some theory behind electricity and electric shocks. A question that's often asked is whether it's voltage or current that's more dangerous. As we'll see, the answer is really both. There are situations where a high voltage can be harmless, such as static electricity, which can be thousands or tens of thousands of volts, yet some low voltages, such as a car battery, can also pose dangers. Current is a more important factor in determining the risk of electric shock. Generally, to cause harm such as cardiac arrest, stopping the heart, requires a certain level of current. Some very approximate ranges of current and their effects are the following, and these assume alternating current. 1 milliamp, or thousandth of an amp, is about the lower threshold of sensation. About 5 milliamps is considered the maximum harmless current. 10 milliamps is the threshold of painful shock and the point at which one may not be able to let go. At 20 milliamps, breathing may cease due to lack of muscle control. 100 milliamps is a potentially lethal shock causing ventricular fibrillation. 200 milliamps can cause severe burns and loss of consciousness, but resuscitation is still possible as the heart stops rather than going into ventricular fibrillation. Direct current is somewhat safer where the current values needed for the same effect are slightly higher, and DC is less likely to cause ventricular fibrillation. By Ohm's law, for a given resistance, the current flow is proportional to the voltage, so a higher voltage generally means a greater current flow and hence more danger of shock. The current also depends on resistance. The lower the resistance, the greater the current. For a person, resistance can be affected by moisture or sweat, whether there's a large or small area of contact, and if it's through the skin or internally via a cut or wound. Any voltage over 30 to 40 volts is generally considered to be capable of delivering dangerous shock currents. So a car battery at approximately 12 volts is generally safe as far as electrocution, but the large currents that can be delivered by a car battery are capable of causing a fire or burns if it's shorted. Radio frequencies, such as those generated by transmitters, have a different set of dangers. Due to a phenomenon called the skin effect, radio waves tend to travel on the surface of conductors. Radio waves given enough power can cause burns or at least heating of the skin. Higher frequencies, such as microwaves, can be more dangerous than lower radio frequencies given the same power level as they carry more energy. Lightning strikes can involve millions of volts and tens to hundreds of thousands of amps. This can be a risk from antennas or even outside power or phone lines as a potential source, so don't work on equipment during a thunderstorm. In North America, the standard is 3 wire outlets with line or live, neutral, and ground wires. Live is generally indicated by a black wire, neutral white, and ground green. A nominal voltage of 120 volts AC is present between the line and neutral. Typically there's a 15 or 20 amp fuse or circuit breaker at the power panel for each circuit. The neutral is connected to ground at some point in the building wiring. Ground also connects to a physical ground or earth, such as a cold water pipe connection. You can think of the current as flowing from line through the equipment and back through the neutral return. A device in a metal case should be connected to ground. Some circuits may have a ground fault interrupter which detects a small current flow, 4 to 5 milliamps, from the line or neutral to ground and shuts off the power. This is designed to prevent electrocution where a person touches a live wire and is grounded, and is often legally required in potentially wet areas like bathrooms or outside outlets. Outside North America, many countries use a voltage of around 220 volts, usually at a 50 Hz line frequency. With double the voltage, the risk of electrocution is higher. Modern devices usually use a 3-wire line cord where the ground wire connects to the case close to the point of entry, but this is not always true, particularly if there's no metal case or chassis, or if the device is double insulated such that there's little chance of the line conductor shorting to metal that a user could contact. Even with 2-conductor line cords, they're typically polarized with a smaller prong for line and larger for load, so that it only fits one way in an outlet. Note that solid-state equipment that internally runs on low voltages still has hazardous voltages inside if it runs on the AC line. Use caution anywhere AC could be exposed, or assume anywhere if not known. Modern designs usually attempt to make the AC wiring less accessible, but older equipment often does not. Battery-operated devices are generally safe from high voltages, but be aware that some old battery-operated equipment, like the so-called farm radios or tube-based car radios, can internally have circuitry to generate high voltages. Finally, I should note some non-electrical risks and dangers when working on old equipment or electronics in general. Soldering presents a risk of burns. Use caution and wear eye protection. Clipping wire leads is also a possible risk of eye damage, and eye protection such as safety glasses should be worn. Solder was traditionally made with lead and zinc, and while toxic, it's more of a risk to the environment when disposed of than to the user while soldering. Lead-free solder is now generally used in modern electronics. It's recommended to use some form of ventilation when soldering, particularly for the rosin flux it contains, which can be an irritant when vaporized. Selenium rectifiers are made from a toxic chemical which can be released if they fail. I'll say more later about replacing these. Another possible chemical danger in older electronics is asbestos. Asbestos pads were sometimes used to insulate wooden cabinets from hot circuitry. This radio has some in between the chassis and the wooden shelf that it sits on. Metal chassis were sometimes plated with cadmium, which can be dangerous if it starts to flake off or if you try to sand or grind it. Luminescent or glow-in-the-dark radio or clock dials typically use phosphorus, but some old radios used radium, which is radioactive. The level of radiation is minimal and does not penetrate the skin, but can be dangerous if it gets inside the body. My general advice on chemical risks such as asbestos, cadmium, radium, and selenium is that unless it's flaking off or degrading, the risk should be low if you limit your exposure when working on it and if it's internal to the equipment and not exposed when reassembled. The general recommendation would be to leave it as it is if it's intact. Check and comply with local regulations if you need to dispose of any hazardous materials such as asbestos. I should also note that some old books on radio repair and electronics lack safety warnings, and some even suggest dangerous practices on the use of chemicals such as mercury or cleaning fluids, now known to be carcinogens. Finally, don't ignore the risk of simply picking up that old boat anchor radio. Some weigh well over 50 pounds, so to reduce the risk of injury, lift safely and get assistance when needed. Now let's cover some guidelines for working safely on old electronics. First, some general rules. Work with the equipment powered off if possible. While it will need to be on for debug or alignment, any visual inspection and tests of parts such as resistors and capacitors can and should be done when powered off. Note that even when powered off, capacitors in the power supply circuit can still be charged to dangerously high voltages. These should discharge within a few seconds, but some circuit designs do not use discharge resistors or they could be faulty. Measure voltages and/or discharge the caps to be sure. Also note that television picture tubes and CRTs in devices such as oscilloscopes can be charged to an extremely high voltage even when powered off. It's very important to discharge this voltage when working on this type of equipment. Televisions in general can have tens of thousands of volts present in the circuitry, and repair should only be attempted if you know what you're doing and have the right equipment. Other general guidelines to reduce the chances of electrocution when working on live circuitry include the rule to keep one hand in your pocket. This reduces the risk of a shock between your hands that will send the current through your heart. Ideally, you should never work alone, although this is probably not realistic to expect everyone to follow. Your work area should be made of a non-conducting material such as wood. Ensure you have adequate space for the equipment under test, test instruments, and any tools. Working in bare feet on a damp concrete floor is a recipe for disaster. Wear insulated rubber shoes such as running shoes, or ideally on a rubber mat, which is also good for reducing fatigue from standing. While not an issue with vacuum tubes, solid-state equipment can be sensitive and damaged by high voltages caused by static electricity. Use a static safe work area with an anti-static mat and or a grounded wrist strap. While there are implicit risks of working on live circuitry, there are some specific shock hazards when working on old electronics. The worst is probably equipment where the chassis is directly connected to one side of the AC line. This means that, depending on how the cord is plugged in, you have a 50-50 chance that the chassis itself is live. This is more common in older radios and in some televisions. Such equipment can be dangerous even in normal use, particularly if there's a way to touch the chassis, such as if a knob is missing on a metal control shaft. The only safe way to work on such equipment is to use an isolation transformer, which I'll cover shortly. The majority of radios and televisions don't have live chassis, but would typically have at least one capacitor between the line, live, and neutral connections to provide a ground path for radio signals. If this capacitor gets electrically leaky, as wax paper capacitors are prone to do, it will now have a live chassis or one that can at least deliver a dangerous shock. Caps should be tested for leakage, or as many people do, just assume they're likely all to be bad and shotgun replace all wax paper capacitors during restoration. Some radios or other equipment may be missing the back cover or never had one at all. This is also a risk in normal operation of the unit if someone might poke their fingers in the back. Larger and more expensive radios, usually that have more than 5 or 6 tubes, use a power transformer that has a side effect of isolating most of the circuitry from ground. The so-called All-American 5 type radios with 5 or 6 tubes usually have no power transformer, so most circuitry is at a high voltage with respect to ground, providing a shock hazard when working on them. An isolation transformer is recommended when working on this type of radio, and pretty much mandatory if it has a live chassis. An isolation transformer has a 1-to-1 voltage ratio, so a unit plugged into it still receives normal line voltage, but it's no longer referenced to ground, so there's less chance of a shock which passes from the radio to ground through a person. You can purchase a ready-to-use isolation transformer or make your own from a suitable transformer. Note that when using an isolation transformer, it should be obvious that there's still a risk of getting a shock between any 2 points on the radio. The one hand in your pocket rule mentioned earlier will help reduce this risk. Also note that if you connect the unit under test to some equipment that is grounded, like a vacuum tube voltmeter, oscilloscope, or signal generator, the unit is no longer isolated and you lose all the protection of the isolation transformer. To avoid this, use battery-powered equipment not referenced to ground, and if you need to connect, for example, a signal generator, don't connect its ground directly to the unit under test ground. If needed, use a small capacitor such as under 0.1 microfarad. When powering old electronics on for the first time, there's a risk of damaging hard-to-replace components due to a short or other bad components. Before powering it on, perform a careful visual inspection and make continuity tests with an ohm meter. The first time it is powered on, it's recommended to use a variac, also known as an auto transformer. It allows you to slowly power up from 0 volts up to the rated voltage. Power it up slowly while watching for any unusual signs like heat, smoke, or arcing. If you have an ACM meter, use it to monitor the current while slowly bringing up the voltage. Note that a variac does not isolate, so you should use an isolation transformer in addition to a variac. Depending on the equipment, it may have significantly high DC voltages present. Check the rating on your DMM or meter and make sure not to exceed the maximum rated voltage. Most modern DMMs are rated to 500 volts or more, but some are not, and allow some margin of safety, as some DMMs may claim to meet CAT standards but may not actually have been approved. So you've picked up an old radio at a flea market, carefully powered it up, and it seems to be working. Is it ready to be put on the shelf and used every day? Not yet. There are some more checks and modifications that you might want to make it safer to use and to extend its life. Before making any changes, there's always the question of whether to keep it original or to modify it. There are a few schools of thoughts here, and I'll share some of my recommendations. If the equipment's very rare and or of historical value, it may be best to leave it entirely original, even if it's not operating. You may even want to not power it up at all to avoid damaging it. It's best left in original condition without even any significant cleaning. For a unit still in original condition, you may want to restore it to operation by replacing faulty or unsafe components, but do so without making any modifications like drilling holes that change the appearance. This is what I would do for a relatively common radio, for example. Would not normally worry if I changed some components to more modern ones, as long as they're not visible from the outside. It's possible to replace some components like capacitors with modern ones, but preserve the original appearance by restuffing the components inside the old ones, or creating paper and wax shells which have the same appearance as the original parts. This is a significant effort in labor, but can be done, and I've done so for a few radios that I own. For equipment that's been heavily modified, which is not unusual for amateur radio gear, you may actually want to undo modifications and bring the unit closer to its original state. Now let's move on to some specific changes that can make old electronics a little safer to use. Sometimes wiring and insulation can be in poor shape, in the worst case having insulation that's crumbling apart. A visual inspection should reveal this, and the relevant wiring should be replaced. Replacing the line cord with a new one is usually recommended for older electronics, particularly if it's a 2-wire non-polarized line cord and plug. Usually this should be a 3-wire line cord, although to maintain authenticity of old radios I often use a 2-wire line cord of similar appearance to the old one, but it will be polarized and thus a little safer. Note that some very old radios had what was called a resistive line cord that contained a voltage dropping resistor. These may appear to have 3 wires even though using a 2-prong plug. They're sometimes referred to as curtain burners, as they can get hot and be a fire hazard. There are ways to replace the cord with a fixed resistor or use a voltage dropping capacitor, but this is an advanced topic outside the scope of what I can cover here. Where the line cord enters the chassis, there's often a rubber grommet. It's good to replace this with a new one if it's not in good shape, as well as some form of strain relief so that pulling on the cord will not pull on the solder joints. I often use a cable tie just inside the chassis grommet. The ground wire from the line cord should be connected to the metal chassis, if applicable, near the point where it enters the unit. Some equipment used a removable line cord. These came in various types, and it can be hard to obtain a suitable cord if missing. They also tend to be 2-wire cords. If there's room, consider replacing it with a standard IEC 320 connector, so that you can use any standard IEC power cord. A lot of old equipment lacks any overcurrent protection. If you plan to use it regularly, it's a good idea to add a fuse or circuit breaker. Even when there was a fuse, old electronics was often sloppy about how the fuse and power switch were wired. In conjunction with a non-polarized line cord, there could be live circuitry inside even when the power switch was off. The correct order of wiring the power circuitry should be AC line or live wire to fuse input, fuse output to on-off switch, switch to load, for example the power transformer or power supply circuitry, then the return from the load goes to the line cord neutral wire. Earlier I spoke about leaky caps across the AC line being a shock hazard. Ideally the replacements for these would be type X1 or Y2 safety capacitors, which if they fail will do so in a safe manner without shorting. I also spoke about replacement of wax paper capacitors. I routinely replace these with modern capacitors, whether they test leaky or not. Electrolytic capacitors, often used in power supply circuitry, should also generally be replaced with new units. The common symptom of a radio producing a loud hum is the most common sign of a bad power supply filter cap. The details of how to replace these could be the topic of a separate video, but in general you want to replace them with units having the same value and voltage rating. The new ones will usually be smaller, and be aware that the polarity is important. Earlier I mentioned selenium rectifiers. These are recommended to be replaced by modern silicon diodes if you plan to use equipment on a regular basis. Depending on the circuit, you may need to add a dropping resistor to account for the lower voltage drop across a silicon diode. Some equipment can benefit from installing an inrush current limiter to reduce the initial heavy power surge when cold, particularly equipment designed when the line voltage was typically close to 110 volts AC, but is now routinely more than 120 volts. As an example, here's the chassis from a typical 5-tube radio from the 1940s. In this case, a Canadian Admiral Model 5B1A, which was actually a combination radio and phonograph for the 1946-1947 model year. I've recapped it by replacing all of the wax paper capacitors with new ones, the yellow caps. I've also replaced the electrolytic filter caps, mounting them on a small terminal strip. The original electrolytics were also under the chassis. If they were larger and riveted to the top of the chassis, I might have left the originals disconnected to preserve the original appearance, or even hollowed out the originals and installed the new caps inside the old cans. This design used a 0.1 microfarad capacitor from the AC line to the chassis. This is a new capacitor now, but the value is a little high as the normal current flow at 120 volts 60 hertz is about 4 milliamps, just within the safe range of current for a shock, but certainly capable of causing a tingling sensation if touched, and enough to make a visible spark if you connect the chassis to ground. If I was to use this on a regular basis, I would probably install a 3-wire extension cord, ground the chassis, and use a slightly smaller value of bypass capacitor. The line cord was replaced with one from a new 2-conductor extension cord that looks similar to the original. This would be typical of the changes I'd make for a radio that I want to restore to working condition, but that I wouldn't use on a regular basis. One final thought, even after making changes as I've described here, I don't recommend operating old electronics unattended, as there's always the possibility of a component failure which could potentially result in a fire or at least damage to the unit. If you do work on old electronics, safety should be in the front of your mind. I hope the information here has given you some insights and encourages you to work safely.